morning, everyone. Welcome to the 𝗳𝗏 network. Today's program sponsored by Photonics Valley Research. I am Srinivasa Gutta, Vice President of Engineering at 𝗹𝗶𝗸's Cadence Design Systems, Hyderabad. Today's topic is about introduction to computer architecture. Computer architecture is a very interesting and a very vast subject. It actually encompasses multiple things which is being taught at university level and also at the master's level, and a lot of research happens in this area because a lot of the CPU design falls into this domain. In terms of the actual computer architecture, today we are going to focus mostly on the aspects related to what is computer architecture, why you need to study about it, and then we talk about what is the performance estimation and performance metrics to be used for measuring different compute systems. Then we talk about data path design, followed by pipeline design, memory architecture, why is it very important in terms of the compute performance, and then we wrap it up with the virtual memory systems. In terms of the textbooks that are required typically in this kind of field, these are the two Bibles for this particular subject. These two books were written in the late 1980s and early 1990s by David Patterson and John Hennessy. These are still considered to be the Bibles for computer architecture. So any undergraduate student or the graduate student should refer to these books for a more core understanding of the subjects. But today, whatever we are going to discuss, the discussion is only going to be at a high level, just to introduce the concepts on these areas, and how do we, once you understand the concepts, how you can actually use these concepts in your understanding further into the subject and making you a computer engineer. So why you have to learn this stuff, right? Why is it very important for you to learn the computer architecture? So the computer architecture, if you learn this subject, the main thing that you're going to look for is, okay, you want to understand how you want to make a decision and provide an expert advice to the people. The second thing is, whenever you want to learn this, you want to call yourself a computer scientist, and you need to make a purchasing decision as you work in a company, and both hardware and software affects the performance. So basically what happens is, if you understand the computer architecture and the CPU design, and also look at, okay, what is the software interaction that goes along with this in terms of compilers, in terms of assemblers, and in terms of the instruction set architecture that is used to define the particular compute engine. So moving on, what is a computer? So a computer can be basically described into these categories, right? The components within a computer are primarily a processor, which is basically the data path, like a adder, subtractor, multiplier, and all the controls that are required to do that execution of that particular arithmetic operation that you want to do. And in terms of input, you have a mouse and a keyboard. In terms of output, you have a display and a printer that you can actually display the outputs. And in terms of the memory, the component memory is primarily referring to a cache. So anytime you buy a CPU, you see there is a cache inside the CPU, how much cache you have and how much memory you have. The main memory is mainly about DRAM. So how much DRAM you have, like a 2 GB or 8 GB or 16 GB, and how big of a drive you have in terms of the hard disk drive or the solid storage device, like a SDD, right? So in terms of the memory, how much memory you have also makes an important choice in the computer architecture. And in terms of the network interface, either Ethernet network or a Wi-Fi network. So they are the primary components within a particular computer. So if you look at this, our primary focus today is going to be on the processor, which is basically the data path, the control, and the cache. What it is within the processor, when you have these bounded elements, data path, which is, as I mentioned, a multiplier or adder or a subtractor, and how do you control it, and the cache memory, which is mainly used for bringing in the data closer to the arithmetic unit. And this implementation is what we are going to focus on today. So, this kind of a diagrammatical representation of major components of a computer that we just looked at. And so, if you look at a program, so what a lot of the engineers do is you have a computer and you write a program. So, when you write a program, what do you do, right? The CPU only understands machine code. It does not understand C, it does not understand Java, it does not understand any of the high level languages. It only understands binary digits, right? 0, 1, 1 zeros. It does not understand anything else. So, this is the machine code is what we call. So, the machine code or the object code is what a CPU understands. So, and how do you, when you move up the ladder from the machine code, which is very impossible to write thousands and hundreds of these lines of code in this binary format. So, we kind of have specific to the computer architecture or the CPU that you are looking at, there is something called an assembly language program. And the assembly language program differs from an x86 processor has one way, MIPS processor or a RISC-V core has one way, and ARM processor another way of assembly language instructions. And this is what we what is called as a instruction set architecture for the CPU. And then above this, we have something called the actual high level language, which is C, Java, and whatever things you learn in the school, right? So, when you have these kind of 3 levels of abstraction, so the main important point here is if you take a C program, for example, and use a C compiler, any C compiler like a GCC or a 𝗳𝗏 or a Microsoft C++, they all have a different way of optimizing the code for a specific computer architecture. So, what happens there is the C compiler actually produces one-to-many code, because every C compiler is unique, and it actually translates. If you write a C program, the assembly language program for that particular computer will be compiled many different ways depending upon the optimization of the C compiler. So, but machine code, for example, is one-to-one, because once you have an assembly language program, it only goes one way into the machine object code. There is no other way. So, once you actually create a program, assembly program, that is it. So, every optimization you need to do from C to the assembly program, that has to happen in the C compiler, and the C compiler quality determines the assembly language program and determines how well the machine object code is structured. Okay. So, advantages, right. So, when you look at high level language advantages, as you know, machine language is very hard to, extremely, not writable at all, because it is all zeros and ones, nobody will understand that. Assembly language, people can still try and write, but not maintainable code, because it is all in the assembly language. And when you write in the high level language like a C or a Java, you gain multiple advantages, right. So, it is not connected to any CPU. So, the C code can be C code, and you can compile for a RISC-V core assembly language, or you can compile to an x86 assembly language, or you can compile to an ARM assembly language. So, basically with this you are getting an advantage, and the maintainability of the code at the C program level or a Java program of these newer kind of programming paradigms that are coming up, it is easily maintainable code. So, if you take the example of the same program that I just showed you, so you have the C compiler and the assembler. So, in terms of the program itself, so if you look at the assembly language line, which is add $2 $4 $2, so this basically translates into add 2 numbers, and the result of those 2 numbers is put back into one of the registers. So, the machine code basically is a encoded version of this particular instruction that is shown below, right. And similarly, if there is another instruction called SW, which is a store word instruction, storing the actual result into the memory. So, that store word instruction is encoded in a very different format. So, basically this encoding and the decoding part is very important in terms of the CPU architecture. How you encode an assembly language instruction and how quickly you can decode determines the efficiency of the CPU architecture. And coming back to our block diagram. So, if you look at the devices itself, the input device is pretty much like, as I mentioned, it's a keyboard or a mouse, and anytime you kind of create a program and compile the program, that goes into the memory. So, basically this is animation that shows, okay, it's a object code that goes from the input device, whatever you have typed in, you compiled, that goes into the memory. And once you have it in the memory, the processor fetches that particular instruction from the memory. So, what we mean fetching is getting, right. So, you basically say you are executing the program. So, you are basically getting that particular program into the processor, one instruction at a time, and then the control unit within the processor will decode this particular instruction, because it understands what is the decoding that I need to do based on the bits and the sequence of the bits that are there. Okay. So, once you have that, so the control unit executes the instructions as directed by the control, right. And now this particular instruction that we are discussing is an add instruction. So, the control unit will say, okay, data path unit adder is enabled, and the adder is basically adding these two numbers and putting back the result. So, what happens next is, once this particular instruction is fetched, that is what the word we use, fetch and then decode, which is basically the decoding of the instruction and enabling the control unit to direct different units within the system to operate on that particular instruction, then which is called an execute stage. So, once it is executed, you again go back to the fetch. So, this is basically the state machine, right. So, fetch, decode and execute is what we have. And within this, so once you have done with one instruction, what do you do again? So, you again go back and fetch the next instruction and go in that sequence. And anytime you have a branch, because the branches or jumps in the code is very common, because you write if loops, you write for loops, you write while loops in the C code. So, all of them become a jump or a branch or a conditional branch depending on something else. So, all of these basically means that you are fetching the instruction that is coming along. It could be the instruction after the current instruction, because it is a sequential instruction, or if it is a branch instruction, you need to go and fetch the branch target instruction, which could be the next one or the later one. Okay. So, once we have this, so the processor organization, to kind of make it comprehensive. So, the control is what we have in terms of the decoding circuitry and decides what happens, and it also instructs every unit in the system to do the operation. And data path is basically the actual data path where you have the adders and multipliers and all these logical functions like exclusive or and or the barrel shifters when you have a shift instruction. So, all of those are part of the data path. And also you have things related to loading and storing the data from the memory, because most of the data is residing in the memory. So, once we have all the things taken care of, so once you have executed the instruction, so there is an output of the instruction that comes out. So, the output actually goes to the memory, and from the memory it goes to the output device. It could be a display, like if you write a cout instruction in C++, so that has to go to the display. So, that happens here. So, the output, the memory output, the string whatever you have in the cout, it sits in the memory, and from memory it goes to the display. Okay. So, now moving on to the second topic. So, now we kind of understood what are the main components and what are the elements of the components within a computer, and how they interact with each other and what is the sequence of interactions. Now we go into the second topic, which is about the performance estimation. So, why is performance estimation important, right? So, when you look at performance estimation, you have multiple CPUs that you buy, or multiple CPU architectures that are defined in the industry, and every time you have to compare one CPU architecture or one computer that you buy versus the other CPU architecture and the other computer that you buy, you need to have a method in terms of how do you compare these two, right. So, at both at the CPU architecture level and also at the broad complete compute system level, how do you make sure you are having a metrics that are defined by the industry, those are standard metrics, and compare apples to apples, not apples to oranges. In terms of the actual performance estimation, there are a couple of things you need to understand before we go into the topic. The first thing is about the clock rate. So, anytime you buy a CPU today, you say it's okay 2.3 gigahertz, 4 gigahertz, 5 gigahertz. So, whatever is the gigahertz rate, that definitely is an important factor in terms of the speed of the CPU and speed of the overall subsystem. So, this is one element of the performance metrics. Definitely, if you see a 2 gigahertz CPU is always faster than a 1 gigahertz CPU. At a very high level, you can say it's 2x faster, but that's not the full performance metric of the full CPU's architecture, right. So, this is one metric that people kind of use, and these metrics primarily depend upon the clock rate, the gigahertz clock rate, and the clock cycle time, which is what we are showing here. So, the clock period is anywhere from nanoseconds to picoseconds, depending upon the clock rate that you are operating in. In terms of defining the speed and the performance, so normally whenever you have a CPU or a computer in front of you, what are you looking for is a response time of the machine. So, you want to do something, you want to open up a Microsoft Word, or you want to open up a large Excel sheet, there is tons of data. The first thing that you understand is, or you want to make sure you are comfortable with, is the response time of the computer, but basically the response time of the CPU. So, response time is something that is defined as an execution time and how quickly it can execute a particular task and how quickly it can give you back the result. So, in order to maximize the performance, you need to minimize the execution time, right. So, basically we have an equation that says performance is inverse of the execution time. So, the lesser the execution time, the better the performance of the computer. It is pretty straightforward in terms of time. So, if you want to compare two machines X and Y, you kind of do a ratio, right. Performance of X by performance of Y is basically execution time of Y by the execution time of X, and you get a factor. So, depending on this factor, if it is more than 1, then X is better than Y. So, this is how you determine the performance at a simple level, at a basic level for the computer, looking at the response times. And then we have something called a throughput. So, the throughput is defined as something like what is the work done in a given amount of time. So, the throughput is very important for any kind of data centers, because once you launch a job or a program into the data center, the data center has to have a large throughput. So, the throughput means how much of the data or how much of the work is done in a given amount of time. So, decreasing response time almost always increase the throughput time, because the faster you are executing the task, then you are ready to take up the next task. That means, if you have a lesser response time, so if you take an example of 1 minute as an example of the time window, if you are able to execute any given task given to a computer, let us say within 1 second for a given task, you will be able to do 60 tasks. So, the throughput is 60 tasks. In the same 1 minute, if you take execution time, the response time of 2 minutes, you are able to do 30 tasks. So, basically that is a relation between the response time and the throughput. So, in terms of the performance factors, so we want to distinguish the elapsed time and the time spent on our task. So, we just now saw the response time and the throughput, which are very good metric to start with, but what is the actual elapsed time, right? So, whenever you see a CPU execution time, so what is the time that CPU spends on executing the task? So, when you say executing the task, when we saw the compute system, what is a computer block diagram, we saw there is a memory, there is a hard disk, there is something that is outside the control of the actual CPU. So, the CPU is executing the task very fast, but let us say an example, a file is there on the hard disk drive, you need to open the file. So, that becomes a I/O task, which means the program that you are looking for, like Excel sheet, is actually going to the hard disk drive, getting the data from the hard disk drive of that Excel sheet and opening the data within the Excel sheet. So, if you look at that example, the I/O could be taking a longer time compared to the actual execution time of the CPU. So, the CPU execution time, when we talk about it, we remove those I/O related or any other miscellaneous wait times of the CPU, because that is not in the control of the CPU. That is basically the whole computer architecture, the whole computer system, how it is designed. Let us say you have a better hard disk drive or a solid state drive like a NAND flash drive, that I/O task will be a better response time or a higher response time, depends on HDD versus a solid state drive, a flash drive. So, because of that, the I/O tasks and the waiting time for the I/O tasks is not considered in the CPU execution time. So, when you talk about the CPU execution time, so clock cycles for a given program, and which does not include the wait times, and then multiplied by the clock cycle time, which is basically the clock rate, inverse of a clock rate. So, it is the same equation with the clock cycle time and the clock rate. So, what we are defining here is you have a CPU execution time for a given program, which is dependent upon the number of clock cycles for a program. At any given time, you can improve the performance by reducing here the length of the clock cycle time, which is basically what we talked about. If the clock rate is 1 gigahertz versus 2 gigahertz, then 2 gigahertz is always better. And then the number of clock cycles for a given program depends upon the assembly language definition of that particular CPU. So, an ARM CPU can have 10 lines of assembly language code, versus x86 can have 12 lines of x86 assembly language code for the same program. Then that is the 2 cycles of additional cycle time. So, that you can say that is 20% slower. So, it is kind of like a number of cycles and the clock rate determine the CPU execution time. And what happens here is when you define the instruction set architecture and when you define the actual assembly language encoding and decoding, not all instructions will be having the same cadence, the same amount of time to execute. Like one way you can think is, okay, you have executed instructions and then multiplied by the average time per instruction, because let us say you take an instruction like a adder, you can do in 1 cycle, but multiplier takes 2 cycles. Because multiplier is little bit algorithmically a tougher problem to do. So, the CPU is taking 2 cycles as an example, but in any given program you have 100 add instructions, but you only have 50 multiply instructions, then you take an average of those. So, basically you can take an example where you have different clock cycles per instruction for different class of instructions, and for a given program you have the frequency of the instructions, and based on the frequency you can determine the actual clock cycles per instructions. So, you take average of clock cycles per instruction. I'll go through that in a little bit on how you compute that. Okay. So, number of CPUs in a clock cycle, number of CPU clock cycles in a program are primarily depend upon the number of instructions for a given program, and then multiplied by the average clock cycles for instruction. Okay. So, this is a kind of an example where it said because in the assembly language programs and the CPU architecture, we define the class of instructions, and this class of instructions in this example we are saying it is A, B and C, and each of them have a different CPI. And if you look at this, if all the instructions in a given program are B type, all of them will take 5 clock cycles. But if you have a mix, a frequency mix, A is 20%, B is 10% and C is 70%, then the CPI, the actual average CPI would be closer to 1, because 70% of the instructions are C class. You have a better probability of reaching the CPI of 1. On the other side, if you have 70% of the instructions are B class, then the average cycle time will be closer to 5. Okay. So, this is another way of looking at it, effective CPI. So, whatever we discussed, so clock cycles per instruction and the instruction count summation over the average. So, it gets the overall effective CPI. And for any computer designer, they always tend to create a CPU architecture where they want this clock cycles per cycle, the CPI, to be equal to 1. So, the target is always getting the effective CPI to 1, because if it is actually executing 1 instruction per clock cycle, that is the highest efficiency that you are able to achieve for this case. So, the overall effective CPI, it varies by the instruction mix. Again, this is again based on the instruction set architecture, the way you define it, and also when you have a high level program, the C compilers also help in terms of creating an effective CPI mix when they compile the code into the assembly language, to make sure there are some optimizations available in the C programs or C compilers, that they take advantage of this phenomena and make sure the instructions are chosen in such a way that you get to a CPI equal to 1. And then the actual CPU hardware also have to make sure we kind of address this and make it a CPI equal to 1 as much as possible when you are making the decisions in designing the CPU. Okay. So, the performance equation then becomes the CPU time is instruction count multiplied by the clock cycles for that instructions, the effective CPI or the average CPI divided by the clock rate. So, this equations basically there are 3 key factors. The clock rate is one factor, the instruction count is another factor, and then the CPI. So, as I mentioned, CPI we try to go to 1 as much as possible. If it is more than 1, it is going to impact the performance. If it is less than 1, it is going to be better for the performance. And then the number of instructions for a given program is also a measure that affects the performance and the clock rate. So, anytime you are comparing 2 CPUs or 2 computers, you look at all these factors, the CPI factor, the instruction counts, and then the clock rate. So, here is a very simple example at the high level. So, as I mentioned, the operations or the class of instructions depending upon the CPU, they can vary. In this case, I am showing an ALU or a arithmetic logic unit. So, in a given program, the frequency, the number of ALU instructions is 50%, load and store is 20% and 10%, and the branch is 20%. So, this kind of like a profiling. So, when you have a program, we can profile the program and see how much of these instructions are within that particular program, and we get this distribution of this operations and its distribution. And now you have the CPI for each of these class of operations. As you can see, the load and store are longer because it has to go to the memory. and then the branch is about 2 cycles and the arithmetic operations are 1 cycle. So, with this example, if you do an effective CPI calculation, the effective CPI calculation comes to 2.2. It is basically 50% is 0.5, 0.5 multiplied by 1 is 0.5. So, you get the ALU is 0.5, the load is similarly 1.0. So, you kind of do the arithmetic of the effective CPI, it comes to 2.2. So, now I have a kind of a computer architecture where I can do 2 ALU operations in parallel. This is called superscalar architecture, where I can have 2 arithmetic units and I can do 1 add and 1 subtract, or 2 adds in parallel, or 1 add 1 multiply in parallel. So, I can do multiple things in parallel. So, if you do that, then your ALU CPI will become 0.5, because you are able to do 2 operations in 1 clock cycle. So, it is basically 1 by 2, which becomes 0.5. So, now your ALU is better. So, it moved from effective CPI of 0.5 to 0.25, and the remaining elements are all the same. Now, the summation of all these average CPI or effective CPI is coming to 1.95. So, when you compare these two, 2.2 divided by 1.95, you can say it is 12.8% faster. So, this kind of a high level example that kind of ties into what we just talked about performance metrics, and this is a simple example that says the second CPU with 2 ALUs in parallel operating is 12.8% faster. Yeah. Now, the third aspect of this particular class is around the data path design. The basic elements, we have seen the performance metrics and how that ties into the actual data path design. So, when you look at the performance metrics, what we have seen is CPI is very important, and making sure that we get to CPI of 1 is the primary objective. So, in the data path design, this particular reference is with a MIPS processor, but can be applied to any processor. This specific example talks about the instructions within the MIPS processor. So, typical implementation has basic memory reference instructions like load and store, and then the control instructions like branch and jump, and arithmetic instructions like add and subtract. So, in a normal implementation, as we discussed, it is called fetch, decode and execute. So, you fetch an instruction from the memory, you decode the instruction so that you understand what needs to be done for that particular instruction. So, what is that instruction going to do, and then execute the instruction and then go to the fetch state for the next one, right. So, except for the jump instruction, there are other instructions also that use the ALU, because the ALU is one data path element that is reused by multiple instructions here, not just the arithmetic logical instructions, but also in case of load, store, if you need to add a number to the address because you have a pointer and then you are actually using a C pointer, and then you are trying to add an address offset to the C pointer, then you use ALU for doing the address computation. In case of branch, you use ALU to figure out if there is a flag that is set, if you do branch equal to, like in a for loop or in a while loop. So, all of that also use ALU. Only jump, which is unconditional branch, there is no condition, only jump does not use ALU, but even the load word, store word, and all the arithmetic instructions and branch instructions tend to use ALU. So, we have one ALU in the CPU that is a multiplexed resource, because other instructions are also trying to use it apart from the arithmetic logic units. So, what is involved in fetching the instruction? So, when you fetch an instruction, so we have something called a program counter in the CPU that keeps track of what is the current program that we are executing. So, the PC typically increments to the next instruction unless there is a branch or a jump. Okay. So, as you can see here, the adder on the top that is shown, that adder is continuously adding +4 to the PC, because it is a 32-bit instruction in this particular case. 32-bit means it is 4 bytes. So, the addition is +4, and every time you fetch an instruction, you are incrementing by +4 to go to the next instruction. So, there is a continuous sequence of fetching of the instructions that happen, and every cycle we are reading from the instruction memory and outputting the particular instruction on the output of that memory. So, within this, if you see the output, so basically the output of the memory, the instruction memory is instruction, and then we have something called a decoding unit. So, the control unit is part of the decoding, and it understands from that instruction what needs to happen, right. So, in this particular case, you have the register file as a data path element. A register file is nothing more than the temporary registers that are defined within the CPU architecture for variable storage locally, so that you do not have to go to the memory all the time. So, these registers are, depending upon the architecture, they can vary from 32 registers to 64 registers. So, in this particular example, we have a MIPS architecture that has 32 registers here. So, each register has a read address and a write address, a read data and the write data. So, these registers can be read and written at a time, and you can see it is a multi-port kind of a register file. So, basically you have the 2 read address and write address. It is called a 3-port register, where I can do 2 read operations and 1 write operation into the register file in parallel. So, when you look at this any of these arithmetic instructions which are called as R format class in the MIPS architecture definition, this R format class has the operands, and if you can see the instruction once it is decoded. So, $2, so the values of the registers are read, and then the particular arithmetic operation is enabled on those operands. So, if you have, let us say, 2 variables that you are adding, and one variable is in the second register, other variable in the fourth register, those 2 registers are read and the data comes out on the read data 1, read data 2, and then the ALU performs the actual operation. Okay. And the register file is also written anytime there is a store word kind of an instruction, or the ALU actually sends the data back into the register file. So, anytime you have a write operation, there is a signal that says register write, that control signal that enables the write. Okay. So, when you execute a load instruction or a store instruction, so I have 2 color codes there. So, the blue is pretty much talking about a load word instruction, and the brown is talking about the store word instruction, and what are the different data path elements that are activated for those 2 instructions. So, when you do a load instruction, if you want to add a particular offset, as I mentioned before, the ALU is a single resource within this particular CPU. The load word instruction uses the ALU to enable or calculate the address offsets. Similarly, the store word also uses this ALU for calculating the address offsets. So, executing the branch instruction is a slightly different data path. So, you have the PC which is PC +4, as I mentioned. Every time you want to fetch something, you are always fetching +4, which is the next instruction. But anytime you have a branch or a jump, you have to follow a different path. So, how do you do that is the instruction, if it is a branch, equal to or not equal to, or an overflow flag. So, those flags are defined in the ALU. So, you compare 2 numbers and say they are equal to, not equal to, or if you add these 2 numbers or subtract it is 0 or a non-zero number. So, all of those are called flags. So, the ALU has a flag here as an example shown as a 0 flag. So, this 0 flag goes into the branch control logic, and the branch control logic is shown on the top, where you are adding a new number to the PC address and keeping it ready so that you fetch that next instruction depending upon the branch. So, if the flag is true, then only the branch will be executed. If the flag is not true, then you do PC equal to PC plus 4. Okay. So, combining all of this together, right, you have all these elements that are combined. So, this one chart where it shows the fetch unit, the instruction memory, the register files, the ALU, and also the data memory that is shown as one unified data path. So, they are the basic data path elements that you need in a given computer design, and in this case a MIPS architecture. So, you have all these elements within this MIPS data path design. And when you add the control unit to this, so as you can see, the control unit is the one that is creating the required control signals like register write or writing into the memory or reading from the memory. So, all those control signals are generated based on this. So, control unit is the essential thing, and actually you can see it's having all the wires or the connections between the control unit into the remainder of the data path elements. So, in terms of the current data path, that whatever we have looked at. So, when you look at the clock cycle and when you look at the actual execution of this particular data path, there is no state element in the data path. So, anytime there is a clock cycle that happens, take an example of the load word here. The load word takes the full clock cycle because that's the longest instruction that you have to execute. And in this case, in a single cycle, the store word is quicker. Let us assume the store word is quicker, or ALU operation is quicker, then you are able to execute within 3/4 of a clock cycle or a half clock cycle. And in this kind of a single cycle kind of designs, which were there in the initial stages of the computer or the CPU being developed, so there are lots of wastage in terms of the clock cycle time, because not every instruction will have the same type of the same type of elements within the data path to be used. So, they could be executing faster or slower. So, depending upon that, it could be wasting some cycles, and the clock cycle you need to define based on the longest instruction that is being executed. So, if your load word is the longest instruction, then your clock cycle rate in a single clock cycle design is defined by that, and you have to waste some time for the remainder of the instructions, and the CPU is considered to be idle in those cases. So, in terms of that deficiency in the single clock cycle, the industry moved into what is known as a multi-cycle data path approach. So, in a multi-cycle data path approach, an instruction takes more than one clock cycle, and what we do there is we divide the instruction into smaller subsets, and each instruction will be using smaller subsets, and it can achieve a faster clock rate because when you divide the instruction into multiple subsets, for every unit, like for example fetch unit, decode unit, if you think at a high level, they will be running at a faster clock rate, and you can achieve a better response time overall. So, this kind of like a high level view of what we are just discussing. So, you have a single clock cycle where everything is happening in that clock cycle. Here we have a same load word instruction that is divided based on this clock cycles. So, in this case I am showing a particular example that we just looked at. I can divide this particular instruction into 5 cycles, and each cycle is doing one operation, like fetch followed by a decode followed by a execute cycle, memory read, and a write back into the memory. So, they are the 5 subunits you can think about in the data path I defined, and load word is using all of this. And if you look at a ALU operation, an ALU operation will only use fetch, decode, and execute, and a store word instruction would use fetch, decode, execute, and write back. So, depending upon the type of instructions or the class of instructions, a part of this multi-cycle data path will be used. So, there is some efficiencies that come up with the multi-cycle, but still multi-cycle also has some deficiencies. So, people in late 80s started inventing something called a pipeline design. So, the next topic is about the pipeline design, because you have a CPU that is operating every clock cycle on a specific task, and when you go through that task, how can you make sure you enable the next task before completion of the first task, right. So, a task in this case is an instruction decoding, executing that we talked about. So, before you could complete that particular fetch, decode, and execute cycle, how can you sequence the next instruction into the data path? And this is more like an assembly line, right. In an assembly line, if you see assembly line of a car, if you make one car and you wait for connecting all the components within the car, it will take 1 day for doing the whole car. But if you take an assembly line of a car, you will see people working in a sequence. So, some people will be fitting the engine, some people will be fitting the tires, and some people will be painting the car. So, all of this happens in a sequence, and the capacity now is higher. So, the pipeline is a similar concept where you are actually increasing the capacity of that particular CPU by executing instructions in parallel. So, this is a representation and a comparison very similar to what we have just looked at for the multi-cycle. So, if you look at the multi-cycle, I am doing a fetch, decode, execute, and the memory and write back for load word instruction. And this store word instruction, I am starting it in the second cycle, because the first cycle the load word is now in the decode stage, but the fetch stage is empty, right. So, now the store word is pretty much can use the fetch stage. So, we are actually fetching the next instruction. So, that particular unit is not busy, it is idle. So, store word is filling that up, and as you can see, they are moving in the sequence. So, any given time we are executing multiple instructions and improving the throughput of that particular CPU. So, a clock cycle is basically the cycle that I am showing there, the clock rate. The clock rate is determined by the slowest stage in the pipeline. So, if my ALU execute stage is taking the longest time, so the execute will determine what is my clock rate. So, this is the high level view and comparing all the 3 ways that we talked about on how a data path design would happen. So, we have a single clock cycle, you have a multi clock cycle, and you have pipeline design, and you can see the comparison point, right. In a single clock cycle, I am taking 2 clock cycles to do 2 instructions, load word and store word, and in a multi cycle I am doing load word, store word, and it is actually taking a slightly lesser time, because as I mentioned, the store word is taking 4, it is only using fetch, decode, and execute and memory. So, it is actually taking it lesser. And if you do a pipeline design, you are basically increasing the throughput multifold, because before you finish the first instruction fully, you are fetching the next instruction and keeping it in the pipeline. So, how do you achieve the pipeline, right? So, if you take the example that we just looked at for the MIPS processor, what we need to do to create a pipeline design. So, it is the same diagram that I showed before. Now, we have introduced a particular element called state registers that hold the information and then it's transferred based on the clock cycle to the next stage. So, in between the instruction memory and the register file and the ALU, you see there are some state elements which are shown, and these state elements will hold the data at every clock cycle before transferring the data to the next clock cycle and move them in the sequence within the pipeline. So, why pipelining makes it easy in the MIPS architecture is MIPS is a RISC based architecture which has fixed length instruction sets. So, it is a 32-bit instruction set and all instructions are in the same length. Very few instruction formats, the formats which I call about the register format or the jump formats. So, the class of instructions is very limited. So, the decoding is very fast because the combinations of encoding in the assembly language lends itself to a quick decoding logic. The memory operations happen only in the load and store instructions. No other instruction is allowed to use the memory. So, if you have to bring something from the memory, you always use load, and if you want to write something to memory, you always use a store instruction. And each instruction writes at most one result into the memory, right. And why pipelining is harder than a single clock cycle design or a multi clock cycle design is because there are things that happen in the pipeline which we have to control. So, primarily those issues that happen in the pipeline are broadly classified as structure hazards, control hazards and data hazards, and we talk about that in the upcoming slides at a high level. So, structure hazard means if you have only one memory, how do you multiplex that memory, right. So, that becomes a structural hazard. At any given clock cycle, if two instructions which are in the pipeline, because the pipeline can hold more than one instruction, if two instructions in the pipeline want to use the same memory, then there is a structure hazard. So, one of them have to wait. So, that is simple structure hazard. And if you look at the control hazards, what we are saying is branches or jumps. So, whenever a branch or a jump happens, so you are filling up the pipeline by fetching the next instruction ahead of time to keep the pipeline busy. But in the ALU, you are saying that okay, now I have a branch to be taken or not taken depending upon the operation that you performed and the flag that is set. So, once you have that, you have to unwind certain things. So, you have to make sure that the pipeline gets stalled and the instruction flow is again resumed after some time. So, that kind of talks about the control hazard. And in terms of the data hazard, what if an instruction input operand is actually depending upon the previous one, right. So, basically there is dependency between the instructions within the instructions, the way the instructions are flowing, that you have a dependency. I will go through those examples later on, but these are the three primary hazards that we see in the pipeline, and there are methods that are defined in all these textbooks on how you control them. Okay. Looks like we have a phone call. Please go ahead. Hello.
Hello. Good morning, sir.
Yeah, good morning. Yeah, please go ahead.
Sir, my name is Mansa, sir. Sir, I was listening to your session about computer architecture, sir. I have a doubt.
Yeah, go ahead.
So, now the computer architecture is how we will be applied in the design and verification of modern VLSI chips like processors or the system on chips, sir. How it will be applied?
How it is applicable? Okay.
Yeah.
Yeah. So what we are discussing today is designing of the CPU architecture and the computer architecture, right? So when you design, so especially let's say you have when you look at the job description for the VLSI design engineer today, let's say you work in a company where you have to design a particular block within a CPU, right? you do the CPU architecture or a block architecture, because the CPU architecture is a very high level, but you need to also do a micro architecture for the block. Let us say you take an example of ALU or the decode logic that I just talked about, right. There will be a micro architecture definition for that block that as a design engineer you have to come up with. So, depending upon like you are an entry level engineer or a mid level engineer or senior engineer, you work on different aspects of that micro architecture definition. A senior engineer would be defining the actual micro architecture for that given block, because that experience is very important. But as a entry level engineer, you will be helping them to create or RTL design for that micro architecture definition, and the verification engineer would verify that particular block and then make sure that it is actually good in terms of the functional bugs, no functional bugs and no functional issues, and then that rolls up into the higher level blocks. And at a SOC level, these CPUs and multiple blocks get stitched together, and SOC RTL design and SOC DV would take care of ensuring the design is proper, and then it goes for manufacturing. So, today if you see most of the design and the verification is focused at the block level and also at the SOC level. So, block level is focused on ensuring that block is proper, and then the SOC level we make sure the SOC is functioning as per the specification. Okay. So, when you look at the pipelining, what makes it easy? We just saw that, and what makes it hard is based on the hazards. So, this is the graphical representation of the MIPS pipeline that we just looked at. This is a different representation with the pipeline stages. So, you have the same instruction fetch, instruction memory, the register files, the ALU, the data memory, and the registers that you have to access again. Okay. So, when you look at this, so you have started with the first instruction, and as you go along by instruction 4, you see the pipeline is full. So, basically you are moving the instruction in the pipeline one stage after the other stage, and as you can see after the fourth instruction or the fourth clock cycle, the complete pipeline is full. When I say complete pipeline is full, every resource, because each stage is a resource that is shown before, like 5 resources and 5 stages. So, every resource is busy after the instruction 4 has been executed, right. And after that, if everything is flowing through normally without any hazards we talked about, you can say that after instruction 4, all the units are busy and you are executing one instruction per clock cycle, right. If you interpolate this to instruction 5, the next cycle also will be fully occupied. So, as I mentioned, so these are the things we need to watch out, because as ideally we want all the units to be busy 100% of the time every clock cycle, but instructions do not lend well in terms of these pipelines. So, you need to have a control with these hazards, and the control unit is also looking at ways in which we can minimize these disruptions due to the hazards, right. So, how do you resolve them cleverly? So, you look at this the same instruction flow. So, in this particular example, let us say the instruction 3 and instruction 1, which is a load word. So, the load word instruction and the instruction 3 are competing for the same memory. That means you have the same resource that is being allocated within that clock cycle. And how do you resolve this? You resolve this by having 2 separate memory elements in this case, which is called a data memory and instruction memory. So, that is why when I showed the initial block diagram, I showed instruction memory and data memory as two separate elements. So, is one structural hazard. So, if you look at the other hazards, so in this case I am showing an example of an instruction that is depending upon the previous instruction data, right. So, the first one, the first add instruction, the destination is $1. So, you added some two numbers and you actually are saying that value of that add is going into the register $1. So, that is this job of the instruction that we are showing in the first line. But if you go down further, the OR instruction is also depending upon the same $1. And if you what we call this as read before write data hazard. So, you are reading the data before the write has completed. So, add is going to complete in the 5th clock cycle and the OR instruction is going to read it, right. So, the subtract instruction and AND instruction which are there right next to it are also depending upon this $1. So, the green ones are okay because you wrote the first one you finished in the 5th clock cycle, and OR and XOR are depending upon that. So, they can read what you just wrote in the first instruction, but subtract and add, which are number 2 and number 3, they depend upon the first one also, right. But if you look at the pipeline, they are reading a old value because they are behind in the pipeline. So, how do you resolve this particular case? You cannot stop the pipeline. The simplest thing is you can stop the pipeline, but if you stop the pipeline, then subtract instruction will not come in quickly after the add instruction. It will take some time, and as you mentioned, as you remember, the CPI has to be 1. So, we need to make sure the instructions flow through the pipeline as quickly as possible. So, the resolving of this hazard happens through something called data forwarding, right. So, in a data forwarding case, so this is a stall. So, just now we talked about the stall. So, if you do a stall, then everything is going to stop and you are wasting those cycles. So, this is a graphical representation of that. And the way to fix this is you forward the data, right. So, how do you forward the data? So, before it goes into the register, the value is available at the output of the ALU, because if you look at the add instruction, add did to an operation and the ALU has the data. But before it goes into the register, we can actually move it in a pipeline and create some muxing logic to forward it to the next two instructions without any issue, right. So, this kind of increases the complexity of the control unit a bit, but at the same time, compared to the previous case where I have shown the stall, rather than wasting those 2 clock cycles, you are able to create this data path and able to resolve the hazard without stopping the pipeline, right. So, that is the advantage that we get with respect to doing all these data hazard detection and then making sure that we have the pipeline going through faster and going through the whole resources that are there in the pipeline. So, other pipeline structures are possible. So, I have shown a simple simple pipeline structure. So, the pipeline structure that we are showing here is if you have a multiplier that takes a longer time, because multiply operation is going to be more complex compared to an ALU operations, the general ALU operations like add and subtract. So, we can think about a pipeline where a multiplier takes 2 cycles, but that can happen in parallel to an ALU and a data memory operations, right. And sometimes the data memory access is slow, then you can create 2 data memory operations, right. So, if a data memory operation is slower and it takes 2 clock cycles, then we can say rather than reducing the clock cycle to fit the data memory access, we can split the data memory access into 2 clock cycles and make sure the clock rate is the same. Okay. So, coming to the summary of the pipeline, So every modern computer CPU heavily depends on the pipeline. No longer we are doing a single clock cycle or a multi-clock cycle kind of CPUs anymore. So every CPU implementation is pipeline CPU design. And the reason why we want to make sure the pipeline CPU design is to get a CPI of equal to 1 and get a faster clock cycle. And CPI equal to 1 will happen only if you are able to look at the hazards that are there in the pipeline and able to ensure those hazards are addressed within the pipeline without creating a stall. So anytime you stall the pipeline, that means you are wasting the resources for that particular clock cycle, and it basically takes more cycles for the stall to resolve itself and also get the pipeline back up and running. Okay. So moving on, so we talked about the basics of the computer. We talked about what is the performance estimation. We talked about the data path design, and we talked about single clock cycle, multi-clock cycle, and the pipeline data path, and how we can resolve the hazards. The next part of the class is primarily focused on the memory architecture, and the memory architecture is also an important aspect of the CPU design, because memory takes multiple clock cycles to load a data variable from the memory to the CPU, and even store a data variable from the memory from the CPU to the memory. So because of this, the memory architecture is also very important. So this is a representation that we saw before, and the memory is in the middle. So the memory performance impact, right? So how does the memory impact? So let's say an example, an ideal CPI of a processor is 1.1, right? Again, as I mentioned before, every time you try to get to 1 is the ideal CPU. In this case, I am saying ideal CPU is equal to 1.1, and similarly, like what we have seen before, 50% of the instructions are arithmetic, 30% is load store, and 20% is control. So the same example that we take, but 10% of the data memory operations within the 30%, right? 30% is load store, and within the 30%, or we are saying is 10% of the operations have a 50 cycle penalty, because the memory is far away. The variable is not in the register file, so you need to go and fetch it from the memory, which takes 50 clock cycle penalty, right? So if you do that and then fit that equation into our CPI equation, right? So you have an ideal CPI which is 1.1, and then you have an average stalls per instruction. So average stalls per instruction is derived from the operation. So you have 30%, which is 0.3 memory operations, data memory operations, load store, and then within that you are saying 10% of them have an IO dependency of 50 clock cycles. So the IO is basically stalling the CPU in this case, right? So IO stall of 50 clock cycles, so that whole penalty is 1.5 cycles. So you are having 10% of the 30% operations having a 50 clock cycles penalty. So the overall number equals to 1.5 cycles. So pretty much on a 1.1 ideal CPI, with this particular mix, we have gone to a CPI of 2.6, just like that. And how do you improve this? Improve this anytime you have the miss penalty is closer to 0, which means closer to 1, then we have again going back to the ideal CPU, right? Because you have 0 miss penalty. Okay. And how do you achieve that, right? So the memory architecture is very critical in this case, not to increase these miss penalties and improve the access to the memory. Okay. So here what we are saying is 50% of the time this processor is waiting for the memory, right, which is very bad for the CPI. So in terms of the memory hierarchy, so we know that large memories tend to be slower, and small memories tend to be faster. And how do we create a memory that gives illusion of being larger and cheaper? and faster. We do this with kind of like a hierarchy called cache hierarchy or a memory hierarchy, and we also do parallel access into the memory. We talk about that in the future in the upcoming slides. So this is a typical memory hierarchy. So in the memory hierarchy, if you see, you have something called a control and a data path that we just talked about, and then we have a cache that we define as something that is nearer to the CPU and taking one clock cycle to get the data from the cache. And then you have something called a second level memory, second level cache, which is also closer to the CPU. And then we have a memory which is a main memory called DRAM. So you have a DDR in the computer that is sitting between the hard disk and the CPU, and the hard disk which is there is a secondary memory. So depending upon where the memory is, you can see how many cycles it takes and what is the size of the memory. So the memory increases in size as we go to the hard disk drive, and it's small in terms of the caches, but in terms of the number of cycles it takes, if you want to go fetch something from the hard disk, it's going to take multiple thousands of clock cycles. But if you look at the cache, it's going to be a single clock cycle access. If you look at a secondary level cache, it could be tens of clock cycles, and a DRAM could be in the hundreds of clock cycles range. So the memory is now structured in this kind of a hierarchy, and within this hierarchy, the access time or the cycle time for that memory varies depending upon where it sits. Okay. So this is another way to look at this same diagram in a pyramid structure. So you have the processor on the top. L1 cache is the closest one, L2 cache is the next level. Nowadays some of the major processors have L3 cache also. That's a third level, but in this case I'm just showing an example of L1 and L2 only, and then the main memory and then the secondary memory. Right. So this increasing distance from the processor. So increasing distance means more access time. The size of the memory, as you can see in the pyramid, the bottom is bigger. You have a large memory pool. As you go closer to the processor, that memory size keeps decreasing. Okay. And in terms of the cache itself, there are some concepts called inclusive and exclusive. So in this case, I'm showing an inclusive. An inclusive cache is basically anything that is there in the L1 cache is a subset of what is there in the L2 cache, and it's a subset of what is there in the main memory and a subset of what is there in the secondary memory. That means you have the data in these memory hierarchies organized in such a way that the data is available, which means if L1 has the data, it's already there in the L2 and main memory and secondary memory. Okay. So in terms of the cache itself, we define the blocks. So the cache has multiple words inside. L2 cache has larger words. Main memory has more blocks, and the hard disk drives have more sectors because the sectors define the number of words in the hard disk drive. So when you look at the memory hierarchy technology, the cache use SRAM. SRAM is a static memory. A static memory means it's actually a 6 transistor design that takes some area. It's a high power, expensive, but it's faster. That's the advantage. And it is static, which means the data will be there forever until you turn off the power. So if you turn off the power, the data will not be there. But as long as the power is available to the CPU, the data will be there in the SRAM. And the main memory uses DRAM technology. So DRAM technology is very high density. It's a 1 transistor cell. It's like a capacitor, 1 transistor cell capacitor. It's a low power, cheap and slow. You can get like multiple gigabytes of main memory. It's dynamic in nature. It needs to be refreshed. The dynamic comes because it's a single transistor. It's a charged capacitor, a switched capacitor kind of a structure. So every time you need to do, we need to have a refresh that needs to happen. we have a call right now. We can go to the call. Hello. Hello.
Hello. Good morning, sir.
Good morning, Amma.
I'm Priya from Maratpalli, sir.
Yeah, go ahead.
Sir, could you please suggest some internship opportunities in computer architecture within the VLSI domain, sir?
Can you repeat the question, Amma?
Hello. Sir.
Yeah, can you repeat the question? Sorry.
Sir, we want some. Can you show some internship opportunities in computer architecture within the VLSI domain?
You mean the internship opportunities within this domain? Okay, so the internship opportunities for CPU design, today I know of like AMD and Intel are two CPU design companies, right, within the industry, and you have ARM design house, which is ARM processors. So these three companies have presence in India, both in Hyderabad and in Bangalore. So there are CPU design teams within these companies that do offer internship programs for university students. So if you go into those companies, definitely you will find some internship level opportunities. Yeah, going to the memory hierarchy. So addresses pretty much in the of this refresh that we need to do every now and then. Okay. So memory performance metrics. So what we look at is what is the latency and what is the bandwidth. So the latency is defined as access time to the memory, and the cycle time, which is time between the requests, and usually the cycle time is more than the access time. So this defines the latency, which is time to access one word of memory, and the bandwidth is how much data the memory can be supplied to the processor per unit of time. That means the data could be like 8-bit, 32-bit or 64-bit, and depending upon the width of the data channel, how much memory we can, how much data we can pull into the CPU or closer to the CPU, and the bandwidth determines the total performance of the memory. So this is kind of like a classical SRAM organization. So you have the array of the memory, which is a cell array that has 6 transistors inside it, and it has a decoding logic and the column selection logic, column address. So based on this, you can store and read a particular value from the SRAM array. Okay. So these are the different elements within the SRAM. So one memory holds a block of data, and the column address selects the actual bit or the bit within the particular word. Okay. And in a DRAM organization, the DRAM has multiple of these RAM cell arrays organized in both rows and columns. So it has more column address space that you can see, and you have more planes of this data arranged in what we call as pages. So the DRAM has page. So each one of the white boxes you see is a page. So there are multiple pages within the DRAM that are organized in a 2-dimensional way. Right.
పోటీ పరీక్షలకు సమాచారం అందించడంలో భాగంగా టీశాట్ నెట్వర్క్ జనరల్ నాలెడ్జ్ అంశాలను ప్రసారం చేస్తుంది. కేంద్ర సమాచార కమిషన్ను కేంద్ర ప్రభుత్వం 2005 సెప్టెంబర్ 11వ తేదీన ఏర్పాటు చేసింది. సమాచార హక్కు చట్టంలోని విధులను అమలు పరచడానికి ఢిల్లీ ప్రధాన కార్యాలయంగా కమిషనర్తో పాటు 10 మంది సభ్యులు ఉంటారు. రాష్ట్రపతి నామినేట్ చేసే కేంద్ర సమాచార హక్కు కమిషనర్లు ఎవరెవరు ఏ సమయంలో పదవిలో ఉన్నారో ఒకసారి చూద్దాం. కేంద్ర సమాచార తొలి కమిషనర్ వజహత్ హబీబుల్లా 2005 అక్టోబర్ 26వ తేదీ నుంచి 2010 సెప్టెంబర్ 30వ తేదీ వరకు పదవిలో ఉన్నారు. కేంద్ర సమాచార రెండవ కమిషనర్ ఏఎన్ తివారీ 2010 సెప్టెంబర్ 30వ తేదీ నుంచి 2010 డిసెంబర్ 18వ తేదీ వరకు పదవిలో ఉన్నారు. కేంద్ర సమాచార మూడవ కమిషనర్ సత్యానంద మిశ్రా 2010 డిసెంబర్ 19వ తేదీ నుంచి 2013 సెప్టెంబర్ 4వ తేదీ వరకు పదవిలో ఉన్నారు. కేంద్ర సమాచార నాలుగవ కమిషనర్ దీపక్ సంధు 2013 సెప్టెంబర్ 5వ తేదీ నుంచి 2013 డిసెంబర్ 18వ తేదీ వరకు పదవిలో కొనసాగారు. దీపక్ సంధు కేంద్ర సమాచార శాఖకు తొలి మహిళా కమిషనర్ కావడం విశేషం. కేంద్ర సమాచార ఐదవ కమిషనర్ సుష్మా సింగ్ 2013 డిసెంబర్ 19వ తేదీ నుంచి
So, memory systems, as I mentioned, the architecture it supports the caches. So, it has the interconnect that comes out of the CPU that goes to the main memory that has 32 bits of data as shown here. And if you increase the 32 bit of data to more bits of data like 64 bit or a 128 bit, that improves the performance and the bandwidth at the bus level, that the data coming into the cache and into the CPU. So, in this case, let us assume there is a 1 clock cycle to send the address and 25 clock cycles for the DRAM access, which is the cycle time, and 8 clock cycles as a access time, right. So, there is a DRAM cycle time and then there is a actual access time for accessing that particular memory, and 1 clock cycle to return a word of data. So, in this case the memory bus to cache bandwidth is the number of bytes accessed from the memory and transferred to the cache per CPU clock cycle. So, the CPU clock cycle is the measure at which the data is getting moved from the main memory to the cache. So, here if there is if the block size is one word is basically 32 bits is what we are saying. So, 1 clock cycle to send the address, 25 clock cycles to read the DRAM, and 1 clock cycle to return the data. So, it takes about 27 clock cycles for one word or 32 bit value to come from the DRAM memory, which is a memory that is shown into the cache and available to the CPU. So, the total number of bytes transferred in this case is 4 bytes, which is 32 bit word means it is 4 bytes, 4 into 8. So, 27 clock cycles. So, the throughput is 0.148 bytes per clock, right. So, this is a very simple example where I am computing the bytes per clock cycle to determine the bandwidth of the bus. Okay. So, 27 clock cycles and 4 words is 4 bytes is what I am transferring within this 27 clock cycles. So, what if the block size is 4 words, right? As I mentioned, if you increase the block size to 4 words, so now you are saying I have 4 words to transfer, each word takes 25 clock cycles. So, I am taking 100 clock cycles from the DRAM and the total comes to 102, right, and these are we are transferring the data one after the other. So, you are taking a 32 bit bus, but I am transferring 4 words at a time. So, I am taking 100 clock cycles. So, the total throughput is 4 into 4, which is 16 bytes divided by 102, which is 0.157. So, the throughput has increased slightly from 0.148 to 0.157, which is a slight improvement. But what if we have interleaved memory access, right? So, as I mentioned, you have 32 bit data bus in the first slide. Now, I am increasing the 32 bit data bus to the memory banking and increasing the number of bytes that I am actually transferring from the main memory. Right. So, in this case I am taking 1 clock cycle to send the address, but I am taking 25 clock cycles for the first read, and then the remaining data that is shown in the blue at the end of that, right, after 25 clock cycles of wait, within 3 clock cycles I am getting all the 4 words of data. So, that means I am only taking 30 clock cycles total. Again, this is similar to the pipelining concept that we talked about, right. So once you fill up, so once you have this interleaving, very similar to pipelining, now I activated the memory, takes 25 clock cycles, but after that every clock cycle I am getting the data from each bank, and I am interleaving each bank to the CPU. So it drastically improved from 102 clock cycles to 30 clock cycles. So now if you see 16 words or 16 bytes are transferred within 30 clock cycles, which means my throughput has increased to 0.533 bytes per clock cycle. Right. So it's a major improvement from 1.148 to 0.157 to 0.533 because of this interleaving. Now going into the cache memory, so memory hierarchy, right? So why does it help? So there are two reasons for this. One is you have a lower level memory, that is a main memory, and you have a memory that is cache, which is closer to the processor. There are two aspects to the program and the instruction set architecture and the way the instructions flow in the CPU. Right? There is something called a temporal locality and a spatial locality. Temporal locality means locality in time. It's about time concept. So you keep most recently accessed data in the cache because there is a high probability that the processor needs the data in the upcoming cycle time. So whatever you are using more frequently, you keep it closer to the CPU in the cache, and that's what the temporal locality property will allow you to do. And spatial locality means locality in space. So move multiple blocks which are in contiguous space into the cache, so that the CPU may be needing it with high probability in the upcoming cycles. So even though you don't need it now, but you are moving multiple blocks which are in close proximity to each other, and those multiple blocks data could potentially be used by the CPU in the upcoming cycles. And we define two parameters here. One is called hit and one is called a miss for the cache. Hit for the cache means the data that is residing in the cache is basically means that the data that it wants is already in the cache. So the data hit rate and the data hit time will be faster. So there is no penalty for the CPU because it's a 1 clock cycle access. If you assume there is no penalty, and if it's a hit, then the data is available and it can read the data immediately without going to the main memory. Right. But if the data is a miss, because the data is not present in the cache, so the pipeline has to wait, and then you have to get the data from the main memory, put it in the cache, and depending upon the bandwidth of the main memory, how quickly you can bring it to the cache determines how long you are waiting. So all of this will play a role in reducing the miss penalty. The miss penalty is mainly about the number of clock cycles that the CPU is waiting, right? So typically we always have hit time is less than miss penalty, because anytime you have a hit, that means you are not incurring any additional CPI penalty for the CPU. How is hierarchy managed? So basically the compiler takes care of register to memory access, and there is hardware blocks which are called cache controller hardware, and there are multiple ways the cache controller operates, and there are multiple different ways of caches in the literature called direct memory map, associative, set associative. So depending upon the type of cache memory that you implement within, you kind of get the cache controller in hardware, and the hardware will manage the moving of the data between the main memory and the cache. So main memory to disks, that particular data movement happens by the CPU OS. So the operating systems like Linux and Windows, there is something called a concept virtual memory that we talk in the next section. So within this, the main memory and the disk movement happens in the control of the software. But the register to memory is based on the compiler, which is again in the hardware. Compiler optimizes it. When it comes to cache to the 15, right? So you have an empty cache, let's assume. You are starting fresh on this particular program, and you have to bring in this data into the memory, into the cache. So when you start looking at the cache and try to access word 0, the address 0, there is a miss, right? So once you have a miss, you bring the word 0 and you go to the next one and try to bring in word 1. It is still a miss, and then you have something called the word 1 coming into the next location in the cache. So similarly, if you proceed, so every time you are trying to access the memory for the first time, you can see the top row 0, 1, 2, 3 are a miss, and once they miss, you are bringing that value into the cache memory. So once you bring it in the cache memory, so now you try to access 4, right, because 4 is again a new one that comes up into the cache. If you try to access 3, the 3 is now in the memory, so in the cache memory, so your penalty is only 1 clock cycle and it's a hit, right. And if you look at the 4, because the 4 cannot fit into the cache because the cache size is only 4 words, you replaced 0 with 4. So you basically, because of the limitation in the cache, when you do the modulo kind of memory, so you replaced memory 0 with 4, right. So now when you try to take to 4, it's a hit again, and then when you try to get 15, it's a miss, and you replace 3 because 15 modulo 4 is 3, and you try to get this into the memory. So there are 8 requests total. You have 6 misses and 2 hits in this particular case, right. So what it means is every time you try to bring in the word, you are trying to place it in a particular location in the cache, and if there is a conflict, you are replacing that particular location. So in this example, when you bring in 4, there is a conflict with 0 because it's the same address, the modulo address. So you replace 0 with 4, and again if you try to read 0 again, you may have another miss, and you have to bring it back again and take away the address 4. So this kind of gives a sequence of hits and misses for a given memory access pattern, right. And this is the architectural representation of the direct mapped cache example. In this case, I am using one word, which is 32-bit per block, and the cache size is 1000 words. So depending upon the address, you have something called a tag. So the tag determines what is the actual address you want to see, and what is the index you want to index into, and see if it's a hit or a miss. So there is a valid information you can see on the left hand side. If the valid flag is 1, which means it's a hit. If a valid is 0, that means it's a miss, and then you need to get the data from the main memory. So handling cache hits. So you kind of look at how do you want to do the read hits and write hits. So basically anytime you have a hit, it's not which is what we want, because the penalty is only 1 clock cycle, and then we can go ideal CPR of equal to 1. Anytime you have a write hits, you have multiple options here for the data. So you can do a write back, or you can do the cache only. A write back means you write the data back to the cache and also back into the main memory, and if you write only the cache, then you need to create one more control signal that says it's a dirty because the data is not in the main memory yet. Okay. So you kind of make sure that you have the cache and the memory to be consistent. Then you can do something called write through cache. The write through cache means every time you are writing into the cache, you are writing back to the main memory also. Okay. So another reference here for the string mapping, the same a different example here, which is 0404. So you're basically ping ponging between 2 locations, right? So if you see here, if you use a simple direct mapped cache, you will find out that you are missing everything, because every time you ping pong, you are ping ponging to the same cache location, which is the same modulo address for the direct mapped cache. You basically are missing, right? So you have 8 requests and you have all 8 misses, which is a very bad thing for the performance. So these are called conflict misses and capacity misses, right? Because the way the direct mapped cache is, it's a modulo cache. So anytime there is a modulo address that comes into the same address location, it's going to remove the previous data and then put the new data. And the CPU fetching this data in the ping pong fashion like 0404, it always sees it's a miss because the data is never there. So the cache misses are primarily classified as compulsory misses, which are like cold start. Anytime you start a new program, there is always a cache miss. And if you look at the conflict side of things, as I mentioned just now, if you look at that particular direct mapped cache example, there is conflict mix because of the address being used, the same address that maps into the same location in the direct mapped cache. And solution for the conflict is to increase the cache size, which is not always ideal. If I increase the cache size like I shown before from 4 words to 8 words, then there will not be any conflict between that 04, but that's always not possible. But you have something called associative cache memories, which take care of these conflict misses. And then you have capacity miss because cache cannot contain all the blocks every time. So you have these capacity misses that happen every now and then. Okay. So taking advantage of the spatial locality, so this is basically the same memory access example that I have shown. You can see this as you move along, you are getting some hits and some misses depending upon what data that you are pulling in. So totally in this particular example, when I have 2 words within each cache line, I am getting 8 requests with 4 misses, and previously if it is 1 word, it is 8 requests with 6 misses. So right now we are improving the number of misses for the cache from 6 to 4 here. And this is basically the direct mapped cache with multi blocks. So the number of blocks have increased. So now we are bringing in 4 blocks. It's the same direct memory mapped, and that increases your hit rate and reduces your miss penalty. So this is the 0404 example where if you prepare something called associative caches, then in this case you have the memories which are associative in nature, and the associative nature will make it in a hit with very limited number of misses for this particular architecture. So in this case you only have 2 misses, but every other access is a hit. Okay. So this is a 4-way set associative. So as I mentioned, when you bring in 0, think about it, it's bringing it to the first bank. When you bring in 4, you're bringing it to the second bank. So the 2 banks are always operating in parallel, and then you can actually access those 2 without any issue for the subsequent CPU requests. Okay. So this is the last section. So we talked about the introduction, we talked about the performance metrics, we talked about the data path, pipeline data path, we introduced the concept of the cache memories. So the last thing that we have for this topic today is on the virtual memory. So virtual memory is a similar concept as a cache memory. So if you look at the cache memory, we use the main memory as a cache for the secondary memory. So you have a DRAM that is there in the CPU in the computer, as well as the hard disk drive, which is a secondary memory. So you think about it, virtual memory concept is a cache between the secondary memory and the main memory. And again, this virtual memory is managed by the software, not by the hardware. So this allows for efficient and safe sharing of the memory among multiple programs, because the concept itself, if you look at it, it kind of manages some of the OS page tables to make it more not visible to everybody, because one program should not be accessing the memory or data for the different program, right? You need to have some kind of user and a supervisor kind of controls, and virtual memory allows you to do all of that within the operating system, right? So again, what makes it work is the principle of locality, because the temporal and spatial data and the way the programs execute in the CPU makes it a viable solution, right? So each program is compiled into its own address space. So an example here is a lot of the people who write C programs, they do something called you want to reserve some memory space for your data, or you define a particular data structure. You do something called a malloc, which is a memory allocation function. And when you say malloc and you say I want 1 MB of data, 1 MB of data space to be allocated, from a OS and the C program perspective, it is 1 MB of data. But actually, if you look at in the virtual memory to physical memory, virtual memory is contiguous in nature, but physical memory may not be contiguous in nature. So the behind the scenes, that 1 MB that you just requested the malloc function to allocate, it's continuous 1 MB that you see in your program, but in real hardware, that 1 MB is divided into multiple pages, and those pages go into different sections of the DRAM. And then there is something called a translation buffer. We will talk about that, that holds these indirections into the main memory on how these 16 MB or 1 MB is allocated. Okay. So this is the example of the address translation mechanism. So you have the virtual address that is given by the OS, and as I mentioned, there is a page table in the main memory. The page table contains what are the blocks of the memory that are shown in those arrows, and a valid bit of 1, which means valid bit 1 means the data is in the main memory. Valid bit 0 means the data is in the secondary disk, which is the secondary memory disk space, right? So we always want to make sure it's a valid bit equal to 1, because the data is already cached in from the secondary memory to the main memory. So very similar concept as cache. So we are converting the virtual address into the physical address, and the physical address is actually accessing the page table and creating the and bringing the data into the main memory. Okay. Okay. So the address translation happens every time. So as I mentioned, the OS is only looking at the virtual address space. The hardware actually takes care of translating the virtual address to the physical address, and the physical address is what the CPU understands, because that's the hard-coded address for the DRAM. Okay. So every memory request that is coming from the CPU would require address translation, right, from virtual space to the physical space. Similar to the cache miss example, the virtual memory miss, anytime there is a miss to the virtual address translation, it refers to something called a page fault. So a page fault or a segment fault happens, and the data from the secondary memory is brought into the main memory, and the page tables are effectively updated, similar to the cache concept. So a TLB is a translation look-aside buffer. So what it means is anytime there is a virtual address, you need to convert that to physical address. So the TLB, which is a translation look-aside buffer, is a faster way to create that translation and then create the physical address map to the cache, so that the physical address is now conveyed to the cache, and the cache can see if it's a hit in the cache or it's a miss in the cache, and then go fetch the location from the main memory. Okay. So a TLB miss. So anytime there is a TLB miss, we don't know it's a page fault or a TLB problem, right? So a TLB miss means the data is already there, but it could be a miss in the TLB, because TLB cannot hold all the translation information. It's more of like a small number of the translation lookups are cached into the TLB. The full translation table is in the main memory. The TLB will only have a subset of those translations. So a TLB miss could be happening because of the full page table is not in the TLB. Sometimes the TLB miss can also become a page fault because the page that you are looking for is also not in the main memory. So that becomes a page fault. So depending upon the type of the miss, a TLB miss is a page fault or a simple TLB miss, the number of cycles it takes for the CPU to wait to fetch those information could vary from tens of cycles to millions of cycles. So it's tens of cycles if there's a TLB miss only, it's a page is already available in the main memory, you just need to bring in the page into the TLB, that's faster. But if it's a miss because the table is not present in the main memory, then the page table have to be restructured by the operating system, which takes millions of cycles. So this kind of talks about the concept of the virtual memory. With that, I thank all of you to be part of this presentation and the class on Introduction to Computer Architecture. If there are any questions on the line, I can take them right now. If not, we can close the session. Yeah. Thank you.
భూమి ఉపరితలంపై ఉన్న పెద్ద భూభాగమే ఖండం. ఆసియా,